Welcome to Chapter 5 and Section 5.1. In our previous chapters, we have been talking about the concept of derivatives, how to compute derivatives, how to apply derivatives and solve problems with them. In Chapter 5, we're going to start talking about how we can undo this process of the derivative. We're going to be talking about the idea of an antiderivative. Through the process of anti-differentiation. And we're going to introduce the concept of an integral today as well. So suppose that capital F of x is a function such that capital F prime of x equals little f of x. So in other words, little f is the derivative of big F. So if little f is the derivative of big F, we say that big F is an antiderivative of little f. Okay, so the derivative of big F is little f, so the antiderivative of little f is big F, right? So we're just going backwards based off of what we're used to. So like for example, the derivative of x squared is 2x. So the antiderivative of 2x is x squared. Okay. Now, you might notice while we've been talking for these few seconds here, I keep saying that big F is an antiderivative, not necessarily the antiderivative. Because the next question, can you think of another function whose derivative is 2x? So there are plenty. You could take, x squared plus 1, something like that. Because the derivative of x squared would be 2x, and the derivative of 1 is 0. So you would just be left with 2x, right? But this constant term here, it really doesn't matter if it's 1 or 2 or 3 or 4 or negative 1,000 or pi or some crazy constant value. If we have constants being added, their derivatives will all be 0. So when we're looking at antiderivatives, there's a level of uncertainty here because when I take the antiderivative of 2x, I get x squared. But I don't know if there was something else here that then turned into a 0. So what we can say is that any function of the form x squared plus c is an antiderivative of 2x. Okay, so any function that has the x squared term plus that constant that we, again, don't know if it was there or not. The value of the plus c, it could be 0. There could be nothing there, but we don't know that. And so we have to be, better safe than sorry, I guess. Right? We need to include this just in case there is a constant value there. So what this creates for us is not just a single antiderivative, but rather a family of antiderivatives. Because now this formula for any real value for c produces different functions, right? X squared plus 1, plus 2, plus 3, plus 4, plus infinitely many different choices of values. So once we know one antiderivative, then all the other antiderivatives have the form capital F of x plus c. So a lot of times when we talk about the antiderivative, usually when we use that term, we're referring to like this specific term, like without the plus c. That's kind of like our just general way of talking about antiderivatives. But technically speaking, there are infinitely many antiderivatives in these families of functions. The only way to get around that is if you have like initial conditions, very specific numbers that need to get substituted in, and we can use those to solve for the c values. but that's something we'll get to later on in the chapter. So if we're trying to take an antiderivative, we want to have a notation in order to establish an antiderivative, some sort of symbolic language that tells us this is an antiderivative. So we say this is where we introduce the indefinite integral. So if all antiderivatives of little f are of the form big F of x plus c, then we write the following. We have the integral of little f of x dx equals big F of x plus c. Okay, so this symbol here is the integral symbol. Okay, it looks like an elongated letter S, kind of. This expression right here, this dx on the back end, this is giving us an indication of what the variable is in the problem. So this indicates the variable to use. Okay. And obviously there's more to it than that, but we're just getting started right here. So let's take a look at an example. So which of the following functions are antiderivatives of this function, 8x cubed? So if we're looking for an antiderivative, okay, so this is the derivative of potentially one or more of these. So if we want to find that, we're going to take the derivative of each of these. So let's see, we bring down the 2, that's 48x, and clearly those are not the same thing, right? So this is not the derivative of big F, so big F is not the antiderivative of this. If we look at g prime, bring down the 4, 8 times 4 is 32x cubed. So we got the x cubed, but this is still not the same. So if we look at the last one, bring down the 4. So for h prime of x, that's going to be 2 times 4 is 8 x cubed. And of course we can see the derivative of h is f. So the antiderivative of f is h in this case. So h of x is an antiderivative of f of x. Right? This is the kind of the core antiderivative here without the plus c or without addition of some other constant. So if we wanted to find the integral of this, so the integral of 8x cubed with respect to x, so dx, that is the antiderivative, which is 2x to the 4th. And then we include that plus c. Again, that's for the general antiderivative term. We're looking at the, again, that uncertainty of whether there could have been a constant there or not. So this is going to be our indefinite integral. And if you want to think about why we call them indefinite integrals, right, again, this is not a definitive, like, numerical solution. So we still have that plus c in there. Now, when it comes to actually finding antiderivatives, right, we don't want to have to Like, we're not just going to be given choices and be like, here, take 100 different derivatives and find the one that matches this. We want to have a more methodical approach to it. So we're going to look at the process of taking an antiderivative by undoing the work of a derivative. So if we look at top of the next page, so we saw that the antiderivative of 2x is x squared. So if we divide by 2, we expect the antiderivative of x to be x squared over 2. Okay, so if you take this, divide it by 2, so that would be x. Right, so we divide that by 2. And if we're just dividing everything by 2, then we would expect the antiderivative to also be divided by 2 as well. So this is what we should be getting for the antiderivative of x. Now, if we check this, so take the derivative of x squared over 2. So we bring down the 2, so that's 2x to the first over 2. The 2's can cancel, and we're left with x, which is precisely what we wanted, right? So the derivative of x squared over 2 is x. So the antiderivative of x is x squared over 2. Okay, so we're kind of making, an educated guess based off of what we already know. So what if we step this up? What if we increase the power? So what about the antiderivative of x squared? So if we took just a cursory guess, if you think about how we take derivatives, right? When we apply the power rule, for example, if I took, the derivative of x to the 5th, I would bring down the 5, and then I would be left with 5x to the 4th. And then if I took the derivative again, it would become x to the 3rd. And the power is creeping down one at a time. If we're taking an antiderivative, I would expect it to go back up. So we would guess, potentially, that it would be x to the 3rd. But when we check this guess, we see that the derivative of x to the 3rd is 3x squared. And so clearly that doesn't match because this one has a 3 and this one doesn't. So we need to adjust. We can get rid of the 3 by dividing. Okay, so again, I'm looking for the antiderivative of x squared. I suspect it would be x cubed, but if it's x cubed, then we get this extra 3 that shouldn't be there. So what we can do is just divide both of those by 3. That one becomes the x squared that we want. And what we have over here is x cubed over 3. That's what we're going for. So try x cubed over 3. So derivative of x cubed over 3, we get 3x squared over 3, cancel the 3's, and that's x squared, which is exactly what we were looking for. So if we look at kind of the pattern of what's happening here, antiderivative of x, x squared over 2. Antiderivative of x squared, x cubed over 3. If we continue this pattern, you could calculate, antiderivative of x cubed would be x to the 4th over 4. Antiderivative of x to the 4th is x to the 5th over 5. This pattern continues, and we can generalize it. So it looks like the antiderivative of x to the n is x to the n plus 1 over n plus 1. Right? This was x to the first, so that's x to the 1 plus 1 over 1 plus 1. This one, for x squared, x to the 2 plus 1 over 2 plus 1. We can check this pretty easily, just like we checked these other ones. So if we take the derivative of this, we do the power rule. We bring down the n plus 1, subtract 1 from the power, that's n, over n plus 1. These objects will cancel and leave us with x to the n. So when we're looking for the integral or the antiderivative of x to the n, we can take x to the n plus 1 over n plus 1, and then plus c. Because again, there could always be that extra constant there, and so we have to include that. Now, this doesn't apply to n values that are -1. So, because if n is -1, so like this, so if we add 1 to the power and divide by that same number, you get x to the 0 over 0, and that's an issue when you have a 0 in the denominator. That specific function is kind of a special case that we'll get into in a little bit. But for any other n values except for -1, this undoing of the power rule is the way to go. So if you're looking for kind of this general strategy for the power rule itself, right, if we took x to the n and did the power rule on it, we bring down the number and subtract 1. So if we are undoing this process, we're going to add 1 to the power. Okay, so instead of subtracting 1, we add 1. And instead of multiplying by that number, we are dividing by that number. So divide by that same number. So that's how we approach the integral of a power function. Now let's look at another kind of special case here. What about the antiderivative of a constant function? Right? So the antiderivative of a constant, we can actually derive this using the power rule. And it's a pretty slick argument. So let's take a look real quick here. So our function is 5. That's the same thing as 5 times 1, right? Don't worry about why I'm pulling this out here out of thin air, but this technically times 1 is still the same thing. If I wanted to introduce an x to the 0 is 1, right? X to the 0 is 1, so this is just like 5 times 1, that's just like 5. So this is the same function. If I take the integral of 5x to the 0 dx, so the 5 is there, I'm going to add 1 to the power and divide by that same number. So this is just 5x. So the antiderivative of 5 is 5x. And if you think about it, right, if we took the derivative of 5x, what happens? The x turns into a 1, and we're just left with 5. So this is the undoing of that derivative rule, of that derivative process. So in general, if k is a constant, the derivative of k times x is k, so the antiderivative of k is kx plus c. Okay, so plus that constant of integration. Let's take a look at a quick example here. Just try out a quick integral. So we have the integral of 3x plus x squared dx. Okay, so if we're undoing the properties of derivatives, when it comes to derivative rules say that a constant multiple doesn't impact the derivative. It also doesn't impact the integral or the antiderivative. So for this one, we're going to have the 3 times the antiderivative of x. We found that one earlier. That's x squared over 2. Plus the antiderivative of x squared is x cubed over 3. Plus c. And then if you wanted to make it look a little nicer, you could do like 3 halves x squared plus 1/3 x cubed plus c, something like that. You don't necessarily have to pull it out of the fraction, but you can. So there's different ways of writing that in its final form. Now, in order to solve problems like this, where you have things like constant multiples, like the 3x, and you have sums and differences, we do need a couple of properties here, just at the top of the next page. So these are the sum and difference properties that say if you take the integral of f plus or minus g, that's the same thing as the integral of f plus or minus the integral of g. So you can split integrals across addition and subtraction. So like with this one, basically what I did was I took these antiderivatives separately from each other, right? So I just kind of split these two and then did them individually. And if you have a constant multiple times the function, you can pull it out and take the integral of the function first and then multiply by the constant. And that's also kind of what I did here. So I basically just ignored the 3 and just did the x squared over 2 first and then times 3. Okay, so constant multiples don't affect integrals. You can even just pull it out and just leave it out there, so it's not going to affect your work. All right. So a few quick examples here. So find each of the following. So we have the integral of x to the 5th dx. So this is the power rule, right? Undoing of the power rule. So we're going to add 1 to the power and then divide by that same number. And then plus our constant of integration. So x to the 6th over 6 plus c, which again, you could also write it as like 1/6 x to the 6th plus c, same thing. Integral of t to the 8th dt. So this is still a power function. The fact that the variable is t now instead of x changes nothing, except for the fact that we're using the letter t. So we'll just take t to the 9th and divide by 9, and then plus c. If we have one like this, with integral of 12x cubed, so you could go ahead and leave the 12 out like this. That would give us, that's x to the 4th over 4 plus c. The 12 and the 4 have a little bit of cancellation, so that's a 3x to the 4th plus c. The way that I like to visualize this personally, because this is x cubed, I know this is going to be a 4. If this number in front, if the coefficient has that value, I can pull it out and move it back up to the top here. So because I know that this 12 is 3 times 4, I'm just going to take the 4, move it up to the power, and all that's left is the 3. So I just took the 4, put it up here, and I'm left with the 3. That's not necessarily, the precise way of thinking about it, because this is what's happening, is you're raising the power and dividing and then canceling. But, that visual just helps me a little bit better picture just taking the 4 out of the 12, and then what you have left over is the 3. Okay? But if that doesn't help you solve the problems, then don't worry about it. That's just my personal style. Let's see, for this one, so we have a difference here, so we can go ahead and split this up. So integral t cubed dt minus, and we can even pull the 6 out if we want, of integral t squared dt. So antiderivative of t cubed, that's 1/4 t to the 4th, minus 6 times the integral of t squared is t cubed over 3. Again, if you recognize that that's going to be a 3, you could pull the 3 out of the 6, and you'd be left with a 2. But either way, you'll get the same thing here when you cancel that. And then we can't forget the plus c. Something like that. Even when you split integrals like this, you only need 1 plus c. If you put multiples, they would just combine into 1 at the end because it's completely arbitrary. We don't have a specific value for that constant of integration, so we just need 1 at the end. We spent the better part of a chapter talking about logarithmic and exponential functions. So we have a couple more just common antiderivatives that come up pretty frequently that we'll need to recognize. The first one, this is that x to the negative 1 case that we talked about earlier. So this is 1 over x. We need to think about kind of the undoing of a derivative. So it's kind of like a game. It's like I had a function, I took its derivative, and it gave me 1 over x. What was that original function? So a function whose derivative is 1 over x, and that would be the natural log function, so ln of x. But we have a little bit of a caveat. When we go backwards like this, there's again, so we have the plus c still, but there's a level of uncertainty because when you start off with ln of x, the input here has to be positive. So when you take its derivative and go here, there's no issues. Going backwards though, this x value could be negative just because of where it is algebraically. Like this could be 1 over negative 2, and that's not a problem, but it is a problem if we take the antiderivative. So the way that we get around this is by taking the ln of the absolute value of x. So this is a little, again, a little twist. When you're taking the derivative the forward direction, it doesn't really matter, but going backwards like this, again, this could have been a negative value, but we need to ensure that it won't be. So we get ln of the absolute value of x plus c. And then we have this really nice one. Remember, the derivative of e to the x is e to the x, right? It's one of those really nice functions that is its own derivative. So its antiderivative is also going to be itself. And then plus c. Okay, so again, plus that constant of integration. So really nice. This is one of the reasons why we like working with e to the x as opposed to other exponential functions, because this one works really cleanly forwards and backwards. So really quick example. So we have integral of 4 over x minus 3e to the x. We can use the sum and difference properties, the constant multiple properties, so I can split this. I can pull the 4 out of the 1 over x, split the negative here, and then pull out the 3. times e to the x dx. So if you're feeling confident and a little more proficient with these integral properties, you don't necessarily have to show splitting it every time or pulling out every time. You can just go through the process a little more quickly. But at least when we're getting started here, it's good to, go slow but steady at first. So this is going to be 4 times the natural log of the absolute value of x minus 3e to the x plus c. All right. Now we're going to take a look at one more example, throw in a modeling problem here, so a little bit of application. So consider the marginal cost function, c prime of x, is negative 0.04x plus 26, where x represents the level of production. At the production level of 150 items, the cost is known to be $6,555. Find the cost function, and then compute and interpret c of 530 and c prime of 530. Okay, so we know c prime, we know the marginal cost function, we're trying to find the original c. So this is where now antiderivatives are going to help us out. So c of x, this is going to be the integral or the antiderivative of c prime of x dx. So we'll go ahead and put the function in there. All right. Now, if we take the antiderivative, this one is going to be x squared over 2, and we can do a little bit of cancellation, so that's negative 0.02 x squared plus 26x. Right, the antiderivative of the constant, it just picks up an x attached to it. And then plus c, of course. Now, if we want to solve any problems with this, having that plus c in there really does put a wrinkle in our calculations, because I can't answer any definitive questions involving these numbers if I don't know what the plus c is. So what we're going to do is we're going to use the known information, the given information, to help us find the plus c. We know that when they sell 150 items, the cost is $6,555. So we know that the cost of producing 150 items is $6,555. And we have the formula right here for the cost. So let's see, cost with 150, so negative 0.02 times 150 squared plus 26 times 150 plus c. These numbers, if you run these through your calculator, you get, that's 3450 plus c equals 6555. And then do the subtraction over here, and you get c is 3105. So this gives us our particular solution, our specific formula. So negative 0.02x squared plus 26x plus 3105. So like I mentioned earlier, with these constants of integration, we don't know whether there is another constant there or not. That's why we include the plus c. But in cases like this, where we have an initial condition, we have some sort of specific number or piece of information to use, we can use that to then solve for that constant. In this case, it was 3,105. So once we have the cost function here, we can use it to compute and interpret C of 530 and C prime of 530. So this is definitely work for a calculator, so you would plug in 530 into here. I will just tell you that's 11,267. And then C prime of 530, we plug back into the derivative up here. That gives us a 4.8. So this formula gives us cost. This formula gives us marginal cost. So when we interpret, let's go ahead and put this into a statement. So the cost to produce 150 items is $11,267. And the marginal cost to produce an additional item is $4.80. So producing 150 items costs a little over $11,000. And then if we wanted to produce that 151st item, it would produce an additional cost of $4.80 based on that marginal cost formula. But this brings us to the end of section 5.1, our introduction to integrals and to antiderivatives. When we come back in the next section, we're going to be looking at more techniques, how we can solve more integrals, different types of functions. We've got a lot of stuff coming up in these next couple of chapters, so I will talk with you all in the next section.